Hello everyone. So today we are going to see the problem implement trie. So this is less of a problem and more of a implementation of a data structure called trie. Okay. Now what is a trie actually? A trie data structure is defined as a tree based data structure that is used for storing some collection of strings. Okay, and performing efficient search operations on them. Okay. Now how does a trie look like? First and foremost, it does have a root node. Okay, a trie node. Now let's say we want to store a string, say this. Okay, this is my name. Now we want to store this string in our trie data structure. How are we going to do it? So each node in a trie data structure has 26 separate spaces. Okay, empty spaces to accommodate each of the characters in the alphabet. Okay, so in one of them we will have a space for s, isn't it? So we will create a space for s and we will store this s into our in this node. Okay, now this node that we created, this will again have 26 empty spaces for the next upcoming letters. Okay, so for o there will be an empty space, so that o will be stored in that node. Okay, now this o will again have 26 empty spaces, so whichever space is belongs to you will be stored there. Okay, then similarly for u there would be 26 empty spaces in the place which belongs to r. We will store r. Okay, similarly we will store I and we will store n. Okay, so this is just a single string. Okay, now this is what basically a trie node looks like. Okay, it has an array, okay, for a length of size 26 from index 0 to 25, which belongs to each of the alphabets. Okay, a to z. Let us consider this lowercase alphabet for this problem. Okay, so this is a node. So when I bring a string, let's say sou, okay, so here we will create a trie node that, okay, this s space has been taken. Now this trie node will look again something like this. This will have all these 26 empty spaces like this. Okay, and whichever belongs to o, we will store that o there. We will create a node there, new trie node there, which belongs to o at the place of o. Okay, like this here. So that's how our trie will keep expanding. Okay, this is how our trie will store the string. Okay, let's say we have this trie. Okay, we inserted this word sourin and we inserted this word tony. Okay, tony. So this s and t, they are part of a single trie node array. Okay, so in the position of s and t we have created these two nodes. Okay, from where these are again another trie. Okay, this is one another trie node. Okay, so like that. Let's say we want to insert this word, okay, into our trie. So are we going to create a separate node for this t? Of course not, because a node which belongs to t, okay, the place which belongs to t is already taken by a tree. Okay, t exists in our data structure, isn't it? So we get to know that, okay, the place of t is taken. So let's go to t. Okay, and we will see in the 26 places that are connected to t. Okay, in it, can we accommodate this o? Let's see. We see that no, the place of o is also taken by o itself. That means to already exists in our trie data structure. Okay, so let's move and come here. Now we want to insert p, right? So we will see in the array, is the position of p taken? We see that no, the position of p is not taken. The position of n is taken, right? But the position of p is empty. So we will create another node for p. Okay, now we finally fill the place which belongs to p. Okay, now we come to p. Now this p will again point to 26 more empty places, right? And we need to fit s into it, isn't it? So we'll see, is it empty? The place of s, is it empty? Yes, it is empty. So we will create a new node for our s. So this is what our trie will look like now. Okay, so what do we understand from this? We understand that if we have a node, it can have 26 children. Okay, all the alphabets, and all these children can have their own 26 children. Okay, a to z. Okay, so that's how a trie is going to work. So I hope that the insertion part is clear. Okay, so for each node we will check if the current letter space is empty or not. If it is not empty, we will move down and see that, okay, this letter is taken this letter is taken. Okay, so for this letter, is the space empty or not? If the space is empty, then we will insert this character, okay, by creating a node, isn't it? And that node will again point to 26 more characters, okay, future characters. So in that we will insert that p if that p is not already there. Okay, so that's how it is working. Now our question says that we have to initialize the try object. Okay, fine. We have to insert, we saw how to insert, and then we have to search. Returns true if the string word is in the try that was inserted before, and false otherwise. Okay, so let's see how this search is going to work. Let's consider this try only. Okay, let's say we want to search the word Tony. Okay, now we will iterate through our try. We will see, okay, is our root node connected to a T? Does the T exist? Yes, it exists. Okay, now we will move down. We will move down. We will see, okay, is our T connected to an O? Yes, our T is connected to an O. Fine. Okay, we'll move down to O. Then we will see, is our O connected to N? Yes, it is connected. What do I mean by connected? That I mean that out of all the 26 places, okay, the space which belongs to N is taken. Okay, because this O is pointing to 26 places, isn't it? And out of them we can see N and P space are taken. So that means the space for N is not empty. Okay, O is connected to a letter N. Okay, that means N is also taken. Then we will see, okay, for the spaces down below, do we have something in the place of Y? Yes, we have Y in the space of Y. That means Y exists. Okay, we finally realize that, okay, our word exists, but there is a catch. We can only tell that this word exists in our try only if initially we had inserted this exact same word. Okay, now what do I mean by that? Let's say we inserted this word Tony, right? But instead of that, let's say we inserted this word Tonys. Okay, let's say this. So Tony is nothing but a prefix, right? A substring prefix of this string, isn't it? So in that case, we won't be able to say that the word Tony exists. Okay, the word Tonys exists, but not Tony. So the thing is, when we insert a word, okay, when we insert a word, the letter using which the word ends, okay, we have to mark it that, okay, a word ends here, a word ends here, ending. Okay, the word ends here. So if the word is Tony, we can only say that the word Tony exists in our try if we already have marked that in Y a word is ending. Okay, if we don't mark that in Y a word is not ending, okay, then we can't say the word exists. Okay, now let's say we had inserted Tonys, okay, and in S we mark that in S a word is ending. So when we search Tonys, when we come to this last letter, we will check that is any word ending here. Then we will see that yes, a word is ending here. It was already marked while inserting, so the word exists. Okay, but if we keep it unmarked, okay, that if we don't mark that a word ends using this S, then we won't be able to say that this word exists. Okay, so this is what searching means. So let's say we have top. Okay, if we search top, this top exists, right? But a word is not ending using top, because while we inserted tops, not top. So while we inserted tops, in the last letter we will mark that, okay, a word is ending in this S. Okay, a word is ending in this S. So when we search tops, we will say that yes, tops exist. But since in P we didn't mark anything, that in P nothing is ending, no word is ending. Okay, we didn't mark anything, so we won't be able to say that top exists. Okay, so this is the thing. I hope it's clear. So just because of this reason, our try node will have a structure like this. Okay, initially it will be false. This is the array. Okay, let's say this is the last node. Okay, let's say in our tops, okay, this node belongs to this S. Okay, it will be connected to it will be connected to O, isn't it? Now in this S we will mark that in this S a word is ending. We'll mark it true. So while we traverse and reach this letter S, this is the node, we will see that is the is complete attribute true or false. We'll see that it's true. That means a word is ending in this S. Definitely the word tops is ending in S, isn't it? But for P, it would be P, sorry. But for P, okay, this is complete attribute will remain false. Okay, so when we search top, we will see that the is complete attribute for P is false. That means no word is ending with the letter P. So top doesn't exist. That means we never inserted the word top, isn't it? We didn't insert top, we inserted tops. That's why we marked S as is complete. We had marked S as true, right? So that's what the thing is. Now let's talk about the boolean starts with method. Okay, returns true if there is previously inserted string word that has the prefix and false otherwise. This one is simple. This is just this one. Okay, how? Let me show. If the word is tops, okay, so our try would have something like this: T O P and S. Okay, let's say we want to see if this prefix exists or not. Okay, so we'll see for T. Does T exist? Yes, it exists. So we will now see, does O exist or not? Yes, O exists. We come to O. From here we will see, is there anything in the place of P? Yes, it is there. So when we are here, we finally see that all the letters in this one are present. Okay, no matter it's not the complete word. Okay, we just need to see that if this prefix exists or not. Okay, so this is just the simpler version of searching. We are just searching that, okay, if this prefix exists or not. Okay, so if this whole thing exists, then we will directly return a true, otherwise we will return a false. Okay, now let's write our solution and we will see the rest of the things on the go. Okay, so initially we need to create our try node class. Try node, it will have a boolean is complete, that okay, in this letter is the word completing or not, is any word completing or not. And it will have, what is it, children, right? It will have an array of size 26. Now let's create the constructor. Try node is complete is initially false, and our children is an array of size 26. Okay, array of nodes. Okay, now let's declare our root. Okay, and let's initialize it inside our try constructor. Okay, new try node. Okay, so this root is going to act as a global one. Okay, we can access this from all these methods, isn't it? Okay, so now comes the work of insertion. So initially we will be at our root, right? We are going to start from the root. Okay, fine. Now we are going to iterate over our word. Okay, to char array and see if node dot children, this is node. Okay, node dot children. Okay, we are accessing this, the array. We will see in that particular index, okay, of the character C. This thing is clear, right? This, I don't think this needs to be explained. If it's a null in that place, that means that letter is not added yet. Okay, in that place what we will do, we will C minus A, we will create a new try node there. Okay, what did we do? If say we have our root node, okay, and our root node is connected to 26 places, isn't it? So in the place of T, we will see is it taken or not. We see that it's not taken, so we will create a new try node here. Okay, we will create a new try node here. Now this will point to 26 more places, isn't it? T node has been created, isn't it? Now what we will do, we will come to that node. Okay, node dot children C minus A. What did we do exactly? When we created this T, we were here, right? From here we created this, isn't it? Now from here we were at here, isn't it? Now we come to here and we will create the nodes down below. Okay, node equals to node dot children C minus A. That means node's child, which child? C minus A child, right? This one. So we are in the child. Okay, so this will continue for the whole string, for all the characters. Okay, after that, node dot is complete equals to true. We will mark it as true. Now what is this? Finally our node will be in the, if the word is tops, okay, at the end our node will be in this letter, isn't it? Because at the last we inserted this letter. okay, and we jump to it. Now we will mark this as is complete. Okay, yes, a word is completing in this letter. Okay, so node dot is complete equals to true. Fine. Now let's do the search. How are we going to search? Just the same. We are starting from the root. We iterate over the array. Now we will see that, okay, if the position, let's say this is our word, okay, we are searching, we are going to search for this word. Okay, now we see we are, let's say, at t. Now from t we are seeing that, okay, if o exists or not. In down below, if o exists or not, if it is not present, that means that position is going to be null, isn't it? In that case, if that position is null, what will you do? You will return a false. That, okay, if we have a t, it's supposed to be connected to o, right? This is our word tops. So if it is not there, that means the word is not there, isn't it? So directly return a false. Otherwise, what we will do, we will jump to that character, we will jump to that node. Okay, just like this. And at the end we will see that, okay, if we have reached in s, okay, we will see that is the is complete attribute true or false. Okay, if it is true, that means a word is ending, that means the word exists, it was inserted. Otherwise, if it is false, that means it was not marked as true, that means this word doesn't exist in our try. It may look that it is existing, but while we inserted it, we didn't mark it. If we inserted, we would have definitely marked it, isn't it? So in that case, return node dot is complete. Okay, just return this, it would be either true or false. Okay, now let's do the starts with. Okay, so just this way it will be the same till here. Okay, we are searching, right? This starts with is nothing but a type of searching only. Okay, if we see that if our word is tops, we come to t, and from t we see that the place of o is null. Okay, that means our word doesn't exist. So in that case, return false. Okay, otherwise node equals to node dot children c minus a. Okay, we are at t, we saw that, okay, o exists. Okay, we jump to o, we are now at o. So from here we will see down below that if p exists or not. Okay, so this way we are coming down. Okay, now finally at the end we will be at s. Okay, so if we were able to traverse the whole string, okay, in what we will do, we will just return true. We don't need to check that is complete attribute, we don't need to check it. Why? Because we are checking a prefix, not the word. Okay, so in tops, if we search to, it will return true. If we search top, it will return true. If we search tops, it will return true. We are not checking the word, we are not searching for the word, we are just searching for a part of it. Okay, if it exists or not. So it's the simpler version of search. Okay, that then return true if we are being able to traverse the whole array and find all of them in our try. Okay, so this is our solution. I hope this works. Let's see. Just a small mistake. We are habituated to writing tree node, isn't it? Yeah, okay. Let's run it. That works really well. So this is the solution. I hope it's clear, like what we are exactly doing. For search, we are checking the whole word. Okay, and in the last letter, we are checking if we have marked it as is complete or not. If we haven't, then this word doesn't exist. Okay, if it is true, then yes, this word exists. Okay, that's how it works. Okay, otherwise, if we are just searching for a prefix, its presence is enough to tell that yes, our prefix exists. We don't need to check any is complete attribute or whatever. Okay, and the insertion part is nothing but coming down and seeing if the position is null. If it is null, create a try node there. Then from down below, move to the next letter and see if it is null. If it is null, create a next new try node there. So like that, come down. Okay, so this is the thing. Now if we talk about the time complexity, it's going to be a big O of n for insertion. Okay, why? Because let's say n is the size of our string. Okay, so we are traversing the whole string, isn't it? We're traversing the whole string. Okay, Now in search also, we are traversing the whole string, that is a big O of n, let's say. And in starts with also, we are traversing the whole string, starts with, let's say. So our total time complexity is big O of n. Okay. Now what about the space complexity? In both search and starts with, our space complexity is going to be a big O of 1, because in these two methods we are not assigning any extra space, but in our insertion we are assigning an extra space of n. Okay, we are assigning an extra space of n because n means n letters, isn't it? N letters, and for n letters means an array of size 26. Okay, that is nothing but n into 26. They are connected like this, like this, like this, isn't it? So n spaces, n arrays, and all of size 26. This can be boiled down to O of n only. So our space complexity is a big O of n. Okay, time complexity a big O of n. So this is the solution. I hope you liked it. If you have any doubt, you can ask me in the comment section. And if you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next one. Bye bye.